All right, let's review your design on Reddit. All right, we have this clone. This is a Arduino. Let's see, Arduino ATMEGA328P a clone. This guy looks like he's doing a little bit of practicing of making design. We're gonna review it for him. We got a typical USB. So you got the USB D plus and D minus, but you have a C connector. Uh, don't want to venture off into the USB-C protocol. That's fine. I'd probably do the same for this level of board. Anyways, standard protection here. No, doesn't look too bad. All right, next we got onto power. We got two voltage regulators. Let's look up these parts. Oh, that looks like a B. 100 milliamps, as well as you got 0.33 on the C1 and zero point zero 0.01 microfarads in the output. That's the manufacturer specifications. That's their preferred specifications. Now you can go across and you don't have to go according to the data sheet 100% of the time, but sometimes you have to make those little adjustments. But unless you got a good reason, I wouldn't deviate from there. You have a linear voltage drop of what, 1.7? A little daring, I'd go with an actual switch regulator, a little bit more power efficient. Whenever you drop it across a linear regulator like this, you lose power. More efficient, a little bit more spendy, but a little bit more circuitry behind it. You've got filters to your output. Take a look at this. Your capacitors, uh, they're different than what the data sheet spec says. I matched the data sheet. Right. Let's do this next voltage regulator. All right. I think I got the right one in there. You got 10 microfarads on the input and the output. Let's see what you got. 10 micro and 100 nano. You might want to match the data sheet, but I'm sure it'll be fine. Let's see what your voltage drop is. All right. Voltage drop is 100 millivolts. Actually, this is pretty efficient. Actually, it can operate, but it's still got to down regulate from 5 to 3. There's some power loss there. Try that switching regulator. You might like it. Use a lot less power, but there's trade-offs, costs. Think you can get away with it especially when it's low voltage, or excuse me, low current, 100 milliamps. So yeah, nothing too troubling so far. Now this one is where it actually tripped me up when I first watched this. And is this switch? I was like, is this backwards? So I looked at it and I'm like, well, this doesn't make sense. You have V bus and then 5 volts. But uh, when I look over here, oh, your V bus is coming here. This is your battery. This is ultimately a bypass through here. It's a low voltage diode. I think it's 400 millivolt drop between there. You're going to burn that up. Less efficient, but it works. I didn't like it at first, but after looking at it and knowing the implications and what you're doing with the design, you just plug it in your USB, or you program your controller and you unplug it and you run off a battery. Well, it's not that bad. There's more efficient ways to do it, but if it's not your main source of power delivery, it's fine. Got a little LED power on. 1K, 0.5 milliamps. That should be about good. Not going to look up the part numbers on those. Now we're going to this serial module. Come on. Go with the USB-C variant. There's a lot more you got to worry about then. Hey, girl. Settle down. So the V bus takes in 5 volts. And then it's saying it's wanting 4.7 and a 0.1 microfarad bypass capacitor. That 4.7 might want to match those. Look a little small for this. One of those is what, a load capacitor for you. And then you also have the 3 volts that go in there. And is that VDD out? I'm not seeing it. So this is interesting. This device on this VDD out actually provides you 3.3 volts, 100 milliamps. This is giving you the same thing that your other regulator is giving you. I understand why you're not using it. You can still get your same GPIO out with removing that 3-volt regulator. I gotta see where else you use that in the design. Maybe I'm jumping it. Save you getting that 3-volt regulator. Yeah, I'd use that voltage source instead of the other one. Come on, use that voltage source and drop this regulator right there. All right, so your pin number 9 is your active reset low. So I don't know what you're doing with this 28, but if you want an active reset low, I tie this 9 to your buttons, to your reset button. And I got to make sure there's nothing else sneaking around in the data sheet you need to hook up. And always, so yeah, on this, I'd check those values. I'd see if you'd use this VDD output voltage in your circuit. There, you might as well. But then you'd have to reconfigure your power, how you have it set up. Summary: check your cap values. Check this pin 28. You really need to reconfigure that. 18 and 19 are 5, and 5 and 4. You get digging into these data sheets. They're 50, 100, 150 pages long. You miss one thing, you're screwed. Now let's go over to the actual microcontroller. All right, so ATMEGA 328. Like, isn't this thing supposed to be retired by now? Retire! Yeah, so AVCC is your high voltage pin. Usually there's some extra filtering you can put on there to make it a little bit more accurate. Then you also have your AREF. The AREF pin goes to your out of your controller. So what that is if you're using your analog to digital converter, you don't want to use that internal value. You can reference that external value. Oh my gosh, this thing's 300 pages long. Yeah, for this AVCC, it got specific design notes in there to pass it through a low pass filter. Right, so for that AVCC, this is your configuration for your ADD converter. That bad boy right there. You gotta set it up like that. I mean, you don't have to. It's just a little bit more accurate. The manufacturers love to go through and tell you exactly how to set up their product. Because if you set it up right, you're gonna use it more. Sometimes you actually need it. Here's that crystal oscillator part. So usually for input capacitor, I do a 1 microfarad as well as a 4.7 microfarad. That add a 4.7 volt capacitor. You'll be good. So he said he calculated this with a PCB toolkit. 12 picofarad. That's within reason. That's what I would think it would be. So I think that's good. All these are tied to analog or digital output. I think that's fine. I don't need to look at that. One thing I'm missing on your voltage regulators is if you're taking those out, add in some ESD protection. So put a diode, TVS diode in there, and you'll be good on that. So the thing is, with 100 milliamps, you got to do your calculations. And when you go through your whole entire setup, you calculate your consumed by each component by your microcontroller. They are recommending 200 milliamps, or that's the maximum. I'd size it a little bit more. So your current design doesn't have enough to satisfy this 200. That might not matter. Depends on your use case, but you're not going to be able to use all of them, all your pins at the same time. Maybe 100 just for the microcontroller and 100 for your simple board layout. It it looks like it's a good layout. I mean, until I dig into the other stuff. Now let's see. From initial reaction, you got your power coming in here. You have your voltage regulators there. You have your VIN, your power input here. So that layout makes sense. So I also notice all the same size capacitors. So the thing about your package on your capacitor that actually provides additional ESD protection. So when your schematic, you show 300 nanofarad capacitors go into your microcontroller, but you have all those the same size on your board. So recommendation, if you have one of those scenarios, you go ahead and you change the size of those because it's going to change your impedance curve, and it's going to provide a low path impedance to ground for any noise that's going through there. So you change the size. Each size has a different characteristic, and it'll dump it to ground. So you have like multiple same size capacitors in a row. Change up the size on those. You'll get better noise reduction in your system. So the layout doesn't look too bad. Here's your buttons. Nothing looking too bad right now. Let's see. I know this is power plane right here. Your 3.3 volts. That's going all the way down here, all the way to here. It's going to the other side of your board. So on your power connections, you want to keep those short as possible. I don't know what flexibility you have in your design, but you can take this 3.3 volts, you put it here, and shift all these down one. That would actually clean that all up. So if you have that flexibility, I would actually recommend that. So I'm paying attention to the power tracing because you want those to be perpendicular with your lines like that. Most of this looks good. These are in parallel right there. Would it affect it? One thing you could do, drop it down to your third layer. I noticed you had two ground planes. Drop it to your third layer and just route it all the way clean through here to this, or move it. That would be my recommendation. You do that, all this changes, and all this becomes a lot more easier for you to route and trace. Now let's check out your 5 volt. This looks good. Goes there. I like your capacitor placement. You did a real good job on your capacitor placement. You put them right where they need to be. I haven't seen one outside of the bounds. It's real nice and tight. Good job on those. See, 5 volt. That looks good. You're overlapping here. You're going in parallel. I take a look where that goes. It goes up to your reset. You're good there. How'd you debounce to your reset? You have your 5 volt there. It's going to run all the way down here where you have that diode. That's fine. That way it powers this. Or excuse me, it doesn't power your. I don't know if you have flexibility in your design. So I'd move these power converters down here, even right next to your USB, and just put all this down here. Makes it easier for routing. You know, you have your 3.3 volt output right next to your 3.3 volt regulator. That cleans it up good. Let's see, anything else? So yeah, it's just biggest issue is this ground or this power. Is it a deal killer? No. I think you're going to be fine. It's not going to be an issue. It does run through here, but then again, if you're using this, you're probably not going to have your USB plugged in. It's not going to cause an issue during operation. It might be just clean up some routing. I don't expect that much noise to come out on this 3.3 volt panel unless they're really driving it. One last thing. So, one helpful tip if you want to help reduce noise is these ground pins that go to the capacitors, your decoupling capacitor, tied to ground like this. So, this is good. The most recommended method is going right here. and right here, but I don't have enough room on that board. So it all depends on if you have room in your design to make these adjustments. Sometimes you have to, and sometimes you get away with it. Sometimes you have to, sometimes you don't. Like this, I didn't go through the VI, connected straight to ground through that one. In summary, I like the USB. I think it's fine. Maybe up your game a little bit and go to the actual USB-C protocol. So voltage regulator, I'd switch it to a switch, and I will go with a higher amperage from there, or get something with 300 milliamps. Your voltage regulator, if you do a little slight tweak, you can actually get rid of this guy and use your voltage regulation off of that. So that's going to change your entire power input. I know, you know, like utilizing what you already have on the board would actually make your job a lot easier. So I did notice you do multi-dual use these pins. So you have your DI D1 and D0. Those are also used as your outputs over here. We can't use them both at the same time, obviously. But you could use one of these other GPIOs that you run it out there, and you get best of both worlds. But you have to communicate that back to your controller. But it's one less component you have to worry about. Uh, Capacitors. Check your capacitors on here. Let's see. You really need to check this DATR or this reset. You've got to have it connected to this 9 pin right there. This isn't configured right here. And you do want to have a pull down resistor, though I don't think this actually is doing anything for you. Your push buttons, put a debounce capacitor and resistor there, tied to ground. You can have a big resistor. See, this looks correct. You did your calculations. I'm not going to double check you on that. Check your load capacitor, or excuse me, your capacitors right here. Stop going blue. One of these should be probably a 4.7 microfarad. Make it a bulk capacitance. Make it a big boy. Schematics, 7 out of 10. There's a lot of things you can fix on it. A lot of optimization. You might not work correctly if you don't have this RST tied correctly. Your Omega looks fine. Some of your capacitors can change up your amperage on your regulator, or switch. Go with a switch regulator.